Okay, let's talk about a massive paradigm shift happening right now in the world of software development. If you rely on AI coding assistants, whether we're talking about Claude Code, Cursor, Codex, or Gemini, you absolutely need to know what's going on with Model Context Protocol, or MCP tools. In this explainer, we're going to dive into how MCP-powered code intelligence engines are completely revolutionizing AI efficiency, taking these tools from slow, expensive text readers and turning them into lightning-fast structural navigators.
So, reality check time. Are your AI agents just burning through tokens? If you've spent any time at all working with AI coding assistants on a medium to large code base, you already know this exact pain point. You ask a complex architectural question, and then you just sit there and wait. You watch the agent run slow query after slow query, you hit your context window limits, and you just blow right through your API budgets. You're basically left staring at the screen while the AI endlessly loops, desperately trying to find the right context.
It really comes down to a stark contrast in how these two paradigms operate. A traditional agent relies on aggressive file searching. It is literally trying to grep its way blindly through your project. It misses cross-file dependencies entirely and wastes massive amounts of tokens. But on the flip side, an MCP-powered agent queries a pre-indexed structural graph of your codebase. It doesn't search, it instantly retrieves the exact architectural context it needs. It's hyper-efficient, and honestly, it is completely changing the game.
Let's break this down further. Part 1. The token burning problem.
We call this the grep and read trap. Think of it like a giant library. If you want to find a specific quote, the traditional AI agent walks into that library without ever checking the catalog. It just wanders the aisles, pulls down random books, and reads the entire book just to see if your quote happens to be in there. That means it is loading full files, sometimes 15,000 to 45,000 tokens at a time, just to locate a tiny 5-line function. It ends up requiring multi-step 10-query chains for a single answer. It completely misses how different files depend on each other, and worst of all, it wastes your compute budget on discovery rather than actual coding.
So, how do we fix this? That brings us to part 2, the knowledge graph solution.
Instead of forcing the AI to read raw text, tools like Codebase Memory, MCP, and GitNexus build a pre-computed relational map of your codebase. They translate your source code into queryable nodes and edges. To do this, they use high-quality tools like TreeSitter to perform AST, or abstract syntax tree, analysis across dozens, sometimes over 100 different programming languages. They then enhance all of that with hybrid semantic type resolution. Basically, this means the graph understands function calls, classes, and cross-service links exactly the way your IDE does. The AI is no longer reading text, it's navigating a highly detailed map. Here is how that map builds seamlessly in the background. First up is extraction, where the tool parses your source code using TreeSitter. Second is storage. Everything gets pushed into a highly optimized local SQL or native database. Third, we have resolution, where it actually links the calls, imports, and inheritances across all your files. And finally, autosync. It watches for file changes using native OS events and updates the graph in real time, incrementally as you type. And the speed here is just staggering. To put it into perspective, a tool like Codebase Memory MCP can index the entire Linux kernel. We're talking 28 million lines of code across 75,000 files in exactly 3 minutes. For your average repository, it happens in milliseconds.
Because the AI now has this map, the efficiency gains are absolutely explosive. Let's look at part 3, slashing AI token usage. 120 times. That is the jaw-dropping reduction in tokens used for structural queries reported by the Codebase Memory MCP tool during their benchmark testing.
Just look at these numbers. When tested on 5 structural queries, the standard grep and read method chewed through about 412,000 tokens as the AI blindly fumbled through the files. The MCP graph, just 3,400 tokens. That is a 99.2% token reduction. One single graph query completely replaces dozens of expensive, time-consuming read cycles. The AI simply asks the graph for the context, and the graph hands it over instantly.
But the innovation doesn't stop there at all. Tools like LeanKG are optimizing this efficiency even further. They use targeted subgraphs and specialized formatting, specifically something they call token-oriented object notation, or TOON. This compresses the MCP responses sent to the AI by another 40%. By stopping the AI from loading irrelevant file data and giving it highly compressed, dense context, it actually delivers 3 times the token efficiency per result compared to baseline code searches. Another tool, GitNexus, refers to this core innovation as pre-computed relational intelligence. By moving all that heavy lifting away from the LLM and onto the client-side knowledge graph, it completely eliminates those frustrating 10 query chains. It feeds the AI the exact callers and clusters instantly. This guarantees that the AI literally cannot miss vital context. And honestly, perhaps the most exciting part is that because the tool is doing the hard relational logic, it enables smaller, much cheaper LLMs to work just as reliably as those massive, expensive flagship models.
We've talked a lot about the mechanics, but what does this actually mean for your daily workflow? Let's check out Part 4, Real-World Speed and Savings.
Let's look at this barrage of benchmarks from the CodeGraph MCP tool across some real-world repositories. Take the VS Code repository, which has around 10,000 files. Using the graph meant the AI made 81% fewer tool calls, but more importantly, file reads dropped from 9 all the way down to 0. The AI didn't need to manually read a single file because the structural context was already served up on a silver platter. This makes the operation 18% cheaper. On the Alamo Fire repo, it was 40% cheaper. The speed and precision here are universal, and if you're operating at an enterprise scale, those cost savings compound massively.
And by the way, this efficiency easily scales to your entire team. Under the old model, every single developer was basically wasting compute power parsing and searching locally on their own machine. But with MCP tools, you can leverage shared graph artifacts. Tools like LeanKG and Codebase Memory MCP allow you to commit a single highly compressed snapshot of the graph right next to your source code. So when a teammate clones the repo, they skip the reindexing step entirely. Or alternatively, tools like Graphify let you run a shared HTTP server, so your whole team points their IDE to one centralized, instantly updated knowledge graph.
To wrap up this explainer, I want to leave you with a punchy tagline from LeanKG that I think perfectly summarizes this entire shift. Stop burning tokens, start coding lean. We are definitively moving out of the era where AI models blindly guess and grep their way through our code bases, and we're entering a new era of absolute structural precision. So, looking at these massive reductions in time, tokens, and cost, are you ready to adopt MCP tools and unlock true AI coding efficiency? Because it might just be the most impactful upgrade you make to your workflow this entire year.